All right. So in today's lecture, we are going to look at the mathematical background of statistical PIV evaluation. So this part is rather mathematical, so we will go a little faster. You can look up the math in the book. There is the Ron Adrian's book and there is Marcus Raphael's book. These notes are taken from Marcus Raphael's book. So the first detailed mathematical description of statistical PIV evaluation was given by Ron Adrian. And later on, it was kind of a beautiful and complete mathematical description of digital PIV was provided by Westerville and Adrian in their seminal book. So remember, this is a handbook. Okay, so this is more practical. So typically when you look at a PIV image, let's look at this particular image. So this is the light sheet and this is the interrogation window and this is the object distance and the image plane from the imaging lens. And the light sheet has got a thickness of delta Z D. Okay, so the interrogation window is right over there and these are capital XYZ is the object plane and small xyz is the image plane. So typically the PIV recordings are subdivided, as we know, into interrogation windows during evaluation. These areas are basically called the interrogation windows. So we will show later that for cross correlation analysis, these windows need not be located at the same position also. Okay, and their geometric back projection will be referred as the interrogation volumes. Now this is a local sample of a PIV image from which a velocity vector is determined and is referred to in the velocity vector of that interrogation window. Its size determines to what degree the recovered velocity value is spatially smoothed. Okay, so these two interrogation volumes are used for statistical evaluation, which measures together constitutes the measurement volume, these two interrogation volumes. Okay. Okay, so this is the interrogation volume and this is the interrogation area. All right, so let's look at the next one. So a single exposure is considered. It consists of a random distribution of particles. Okay, so which correspond to the following pattern of n tracer particles inside the flow. So this gamma that you see over here describes the state of ensemble at a time t. Xi, capital Xi, is the position vector of the particle I at time t. All right. So if you go back once again, you will see that, okay, these are the capital XYs and, this is basically an ensemble, state of ensemble at a particular given time t, where xi is basically the position vector, okay, position vector xy of the particle at time t. The lower case refers to the coordinates, the image plane now, okay. So this lowercase x, again, go back to the figure, you will see that this is basically the small xy. The small xy, the lowercase, refers to the coordinate in the image plane. So how are they related? Capital XY is equal to small xy divided by m and capital YI is equal to small yi divided by m. So the particle position and image position are related by a constant magnification factor which is given as m. All right, so this is given as m, the particle position and the image position. So this should not be very difficult to comprehend. Now let us look at the image intensity field. This is where things becomes a little bit complicated. So, the mathematical representation of the intensity distribution on the image plane is what is to be determined or what is given. Okay. So what is the image? It is assumed that the image, okay, can be described by a convolution of two things. One is the geometric image and the other one is a point spread function, which is the impulse response of the image system. So for infinite small particles, and if we assume that our lenses are aberration free and well focused, etc., etc., so the amplitude of the point spread function, which is the impulse response function, is basically described by the first order Bessel function, which is also called the Airy functions. This we already did a little earlier. So what is it? The image is a convolution of the geometric image and the impulse response, that is the point spread function. So for infinite small particles and for perfect lens assembly, this is described by a first order Bessel function. So the Airy function is called the first order Bessel function. So in the analysis, we are going to assume that the point spread function of the imaging lens, which is tau x, is Gaussian versus x and y. Okay, so we are going to say that this point spread function of the imaging lens is Gaussian. So the convolution product of tau x with the geometric image of the tracer particle at a position xi therefore describes the image of the single particle located at capital Xi. So capital Xi is the actual particle which is located at capital XY in the object plane. So here what we are assuming that if we convolute the product, if we multiply the tau x, which is the point spread function, which is Gaussian, with the geometric image, okay, of the tracer particle at the image plane, which is small xy, together this convolution will describe the image of the single particle located at capital XY. So therefore, we restrict the analysis to infinitely small geometrical particles, which would be the case for all small particles imaged at small magnifications. So therefore, what we can do, we can use the Dirac delta function shifted to a position xi to describe the geometric part of the particle image. So the geometric part of the image, so we already know the spread function is Gaussian. Now the geometric part of the image for small particles and at small magnifications is described by the Dirac delta function shifted to that particular particle position xi. All right. So the schematic which is shown over here, so if you look at the schematic over here, so this is an example of an intensity field with small xi. So therefore, we use the Dirac delta function shifted to small xi to describe the geometric part. So the image intensity field therefore becomes I, which is a function of x comma gamma is equal to the point spread function, which is tau x, multiplied by this term where delta is nothing but the Dirac delta function, which is shifted to the position of xi. So this v naught xi is a transfer function, basically giving the light energy of the image of an individual object I inside the interrogation volume vi, and its conversion into an electronic signal. So tau x is considered to be identical for every particle position. That means the Airy disk is the same for all particles. All right. Only the delta x minus xi is basically shifted to that corresponding particle locations small xi. And what is v naught xi? It is just a transfer function which is basically the light energy of the image of an individual particle and its conversion into an electronic signal, and that's about it. All right. So in many situations, what happens is that we assign different weights to different locations inside the interrogation window by multiplication of the recorded image with a kernel, or weighted kernel basically. So we assign different weights at different points in the interrogation window. Further, we assume that Z is the viewing direction, okay, and the light intensity inside the interrogation volume is only a function of capital Z, and the image intensity finally analyzed depends on X and Y only due to the weight function. Okay, so if Z is the viewing direction, the light intensity inside the interrogation volume is only a function of Z. So therefore, V naught X just describes the shape and extension and location of the actual interrogation window. So what is V naught X? It's a multiplication of W naught XY into I naught Z. So I naught Z is the intensity profile of the laser light sheet in the Z direction. Okay, and W naught XY is the interrogation window function geometrically back projected into the light sheet. This is also assumed to be so that Gaussian intensity profile is assumed, the laser light sheet intensity profile is assumed to be Gaussian, where Z naught is the thickness of the light sheet and IZ okay, is basically the maximum intensity of the light sheet. Okay, this we have already covered a little bit earlier, that why the laser intensity is Gaussian. And W naught xy, okay, which is the interrogation window function, geometrically back projected, is described by a similar way by a Gaussian window function with a maximum weighting, which is Wxy at a position x naught, y naught. All right. So this is also given by this particular relationship. Okay. So this is a weighting function, and because of the viewing angle, we are having this weighting function as well as the laser intensity sheet profile. This is also, remember that the interrogation window, different locations of the interrogation window is assigned different weights. All right. So therefore the V naught, which is describes the shape, extension, and location of the actual interrogation window, is a multiplicative of two terms. One is the laser intensity profile, which is Gaussian, which basically spreads. Okay. The other one is a Gaussian window function, which has got its peak location at x naught, y naught. So this is the thing that we actually see over here. All right. Okay, and tau x, remember once again, is a point spread function or the Airy function. Okay, so the intensity distribution, if the intensity distribution is like a top hat function than a Gaussian function, then the digitized recording are commonly interrogated with rectangular windows. In that case, first and foremost, instead of these complications, we write that I naught z, which is the laser intensity profile, is equal to Iz, which is the maximum intensity, because it's now a top hat profile. Remember, it's not a Gaussian anymore. It's a top hat, means it's a constant profile. So if this is z minus z naught is less than equal to delta z naught by 2, this is Iz and it is 0 everywhere. So this is the intensity distribution, which is closer to a top hat function. Okay. Similarly, therefore, the window function can also be written in the same way, where it is Wxy within a certain band and it is 0 everywhere else. Okay. So now, therefore, what will happen, the factor I naught z represents the amount of light that is received by the particle inside the flow, and Zi minus Z naught is from the center plane of the laser sheet. Delta Z naught is a laser sheet thickness. Delta X naught equal to small x naught divided by M. So all these terms are actually present over here. Okay. So now what we see is that if you take a look at this particular equation, okay, which is so if you take a look at this particular equation, okay, this is what we already discussed. You can transform this into this particular form. Okay, what you see over here. Okay, so here there are many things, which we'll come across a little later, but this is the form that is to be used. All right. So now we go to the extent of spatial estimators for mean value and the variance of the image intensity field, because this is the one that are utilized for the normalization of the cross correlation. So the spatial average is defined as this. So this bracketed terms is basically, it denotes an average, and AI is the interrogation window. So basically you integrate the image intensity across the interrogation window and divide it by the interrogation window size. Okay, so if you look at this particular expression, this is what we derived. Okay, and if you take the mean of this, this is what you are going to arrive at. Okay, so you can do these calculations. Again, this is a spread function, and V naught is basically the transfer function. Right? So the mean value of the intensity field, therefore, which is say mu1, is basically this average of this I field. And if you take the V naught x out, it is an interrogation of the tau x minus xi over the entire area. This is an approximation. Okay. Now, if we look at the autocorrelation of the single exposure intensity field, that means it is a correlation of the intensity with itself with a little bit of a S, or with a little bit of a separation. So you take the intensity fields and you basically multiply it with a separation vector. I mean, you evaluate the intensity field with a different separation vector, and then you calculate the total intensity. This is called the autocorrelation of a single exposure intensity field. Okay, so what it happens is that if you take a look at this, then you multiply these two terms, and this is the integral. Because the integral comes out of the integral arises because of the bracket, which is basically the mean averaging. So you can see one in this case is tau x minus xi, the other one is x minus xj, plus there is a factor s, which is the separation vector. This is I over I from 1 to n, and this is j over 1 to n. So just remember this. This is the mean value of the intensity field, and this is the autocorrelation of a single exposure intensity field. Okay, so these are the spatial estimators. So where do they come from? They come from these. All right, and the V naught, we already estimated what the V naught will be by looking at these terms, right? And by assuming top hat profiles and whatnot. Okay, the math is a little cumbersome, which you can go through it. So by distinguishing the I not equal to j terms, which represents the correlation of different, this is not equal to. So let's just put that not equal to. Okay. Okay, not equal to j terms, which represents basically the correlation of the different particle images, and therefore randomly distributed particles and randomly distributed noise in the correlation plane. And I equal to j terms now represent the correlation of each particle image with itself. So therefore, if we look at this particular situation, which is Ri s comma tau, okay, we write it. This is once again the expression where you are separating the two terms. This is I not equal to j, and this is I equal to j. All right, so xi and xj are equal, and there xi and xj are not equal. So I not equal to j are the terms which represents the correlations of different particle images, and therefore randomly distributed noise in the correlation plane. And I equal to j represents the correlation of each particle image with itself. Okay, so therefore, if we look at this, and Adrian did this, and Ron Adrian, and then we actually follow this particular decomposition. So this is the total autocorrelation function. So this autocorrelation function now has got three parts. One part, this RC part, is the convolution of mean intensities of I, okay, mean intensities of I, and RF, which is the second term, is the fluctuating noise component. Both of these arises from I not equal to j terms. Okay, again not equal to. Sorry, it came out like this. Okay, not equal to j terms. Okay, then the RP finally is the self correlation peak. Okay, which is located at the position 0, 0 in the correlation plane. It results from the component that correspond to the correlation with itself, or I equal to j terms. So the first two terms, RC and RF, RC is a convolution of mean intensities, and RF is the convolution of fluctuating noise, both when I is not equal to j. RP is the only term, okay, which is the self correlation peak where I is equal to j. Okay, so these are the two things, these are the things that one should remember. Okay, so this is how the autocorrelation peak actually looks like. Okay, it shows a very central RP, and then you can see RC plus RF terms are all there. Okay, it shows basically this is what we call a noisy floor. So R and RP is a peak, okay, while everything else is kind of distributed. Now for a Gaussian particle image intensity distribution, this tau x, which was basically the Airy function or the spread function, is given as this. Okay, R tau is again a Gaussian function. Okay, let's assume R tau is a Gaussian function with a width that is root over this is d tau. This is the same as this. Okay, so therefore RP is written as this, because it's a multiplication with a point spread function, which is essentially what we have over here, this s bar square. okay, and r tau, okay, is given as this. So the maximum r tau is located at delta s, which is the separation vector equal to 0, and the characteristics of its shape is given by the particle image shapes. So the r tau, okay, so the r tau that you see over here, let's move a step back. Okay, so the r tau that you see over there, okay, is basically located at the central, okay, peak. This is the rp, okay, and the characteristics of its shape is given by the particle shapes. Okay, so this is how the autocorrelation function actually looks like. Here everything is kind of taken to be Gaussian, as you can see, because this is also taken to be Gaussian, okay, the Airy function, and then you have the Gaussian function with a width of delta tau, delta 2 or root 2 d tau, okay, not delta tau. All right, so what do you see? So when you are talking about the correlation peaks, RP and RF, okay, so RP, for example, the correlation peak, okay, and an RF, which is the from the fluctuating noise, okay. So if you look at this image and then the autocorrelated image, okay, so RP is basically R tau multiplied by this V naught square xi. The correlation peaks RP and RF occur at locations which are given by the vectorial differences between the particle image locations. Now you can see that their strengths are proportional to the number of all possible differences which result in that location. So now, as there are 3 vectorial differences now, okay, which contribute to R, okay, the peak of RP is 3 times stronger in this example than other peaks. Okay, so that is what we are, what we get out of this. Okay. So for intensity fields with 0 mean value, the autocorrelation equals to the autocovariance. Okay, so autocovariance CIS is equal to this. An estimator of the variance of the intensity field can be derived by this particular method. Okay, so you understand the correlation peaks RP and RF occur at locations which are given by the vectorial differences, right, between the image locations, and their strength is proportional to the number of all such possible differences. Okay, now 3 vectorial differences contribute to RP, and therefore the peak is 3 times stronger in this example than any other peaks. So this is for a 3 particle kind of a system, okay, that you see. So the cross correlation of a pair of singly exposed recordings. So the PIV recordings are evaluated by locally cross correlating 2 frames of single exposure of tracer ensemble. So again, what you have, a constant displacement d of all the particles inside the interrogation volume, remember this is the object plane, is assumed. So the particles during the second exposure lies at a distance xi plus d, which is essentially has 3 components. This we have seen already. Now we assume that the particle displacements are in the image displacement. We have basically, small d, which is the magnification into the capital D. Now here we have neglected the out of field velocity components, as you can see. Okay, so the following representation of the image intensity field for the second exposure. Remember, for the second exposure has an added term which is d over here. Okay, so this d is the image displacement, small d is the image displacement, and it is related to the actual displacement, which is the constant displacement within the interrogation volume. Remember, all particles in the interrogation volume are kind of assumed to have a constant displacement, which is capital D. Okay, and so this is what you get. V naught prime x defines the interrogation volume during the second exposure. Right, so this you can see, this is xj plus capital D, which comes from that, the transfer function, and then tau is basically the point spread function. Here the small d is actually the image displacement in the second exposure. So we first consider identical light sheet and windowing characteristics. So it's the same, the cross correlation function of these 2 interrogation windows are given as this. Okay. So this is the interrogation, S is a separation vector, which is used in the plane, and then analogous to the previous procedure that we used, we get this. Okay, by distinguishing that I is not equal to j terms, which represents the correlations of differently randomly distributed particles and therefore mainly noise in the correlation plane. And then the I equal to j terms, which contains the displacement information, we get these two values. One is I not equal to j, which is basically the correlation of differently randomly distributed particles and mainly noise. The other one is basically so this is I not equal to j, and this is I equal to j terms. Again, we decompose them into three parts, where Rd is represents the component of the cross correlation function that corresponds to the correlation images of the images of correlation of images of particles obtained from the first exposure with images of identical particles obtained from the second exposure, which is I equal to j terms. The rest of the terms, as we know, one is the mean and one is the random fluctuations, both arising of I not equal to j terms. So Rd is the term which represents the component of the cross correlation function that corresponds to the correlation of the images obtained from the first exposure with identical images of the particle obtained from the second exposure with I equal to j terms. Okay, so this is the cross correlation method. Okay. Okay, so this Rd is basically therefore given as this. Okay, hence for a given distribution of particles inside the flow, the displacement correlation peak reaches a maximum when the separation vector is equal to d. Okay, so this location of this maximum yields the average in plane displacement. Okay, and thus U and V components of the flow inside. This is the most important thing that we will take out. Okay, nearly, as you can see from these images, nearly the same correlation peaks occur as the autocorrelation, but the locations are displaced by D. Okay, and when S equal to D happens, we get the maximum displacement peak for a given distribution of particles. You get the displacement correlation peak reaches a maximum for S equal to D. The location of this maximum actually yields the average in-plane displacement. Okay, and in this case, so this is exactly what happens. This is how the cross correlation technique actually works. So it is, the peaks are nearly the same as autocorrelation for this 3-particle exposure, but the locations are displaced by D.